Welcome, ChemComm. Up to this point in time, we've talked about atoms, their parts, and how they make different bonds. Today, we're going to start investigating the process of how atoms combine in chemical reactions. Let's get started. One of the misconceptions we've talked about is that sometimes students think that atoms or matter disappears in a chemical reaction. We start with something like a log of wood, and over time, it's not there anymore. So the matter must have been destroyed. But the law of conservation of matter tells us that matter can't be created or destroyed. It can be broken apart, rearranged, and bonded to other atoms, but it's still there. Atoms don't just disappear. We put gas in the gas tank, and as it burns, it creates gases like CO2 and H2O, and those exit through the exhaust. But the matter, the carbon and oxygen and hydrogen that was in the gasoline is still there. It's just dissipating into the atmosphere. Because of this law of science, we need to make sure that when we're looking at a chemical reaction, the atoms that we start with equal the atoms that we end with. The reactant and product sides of the chemical reaction need to be balanced. So if we look at an example here of burning coal, we see that we're starting with carbon and oxygen, O2, and when we get finished, we still have one atom of carbon on both sides and two atoms of oxygen on both sides. We've rearranged it into a different molecule, but the same number of atoms. In the same way down here at the bottom, we started with two atoms of copper and one molecule of oxygen. And when we are done, we have two molecules of copper oxide, but we still have 2 and 2 on both sides. So if we're going to learn how to balance chemical equations, we need to identify some of the parts of that chemical equation. Some of these we already know. Subscripts are a number printed below the line of a chemical in order to tell us how many atoms of a specific element we have. So you can see down here in the graphic these 2's next to hydrogen and oxygen. They tell us we have 2 atoms of oxygen bonded together and 2 atoms of hydrogen bonded together. On the right side we see we have 2 atoms of hydrogen. There is no subscript next to this oxygen and water, and that tells us we just have one of them. Subscripts indicate that those atoms are bonded together in a molecule. Coefficients, on the other hand, are big numbers in front of formulas, and they tell us how many molecules of that compound we have. So if you look here, we see a large 2 in front of this hydrogen gas. That's telling us we have 2 hydrogen gas molecules, just like on the right side where we have 2 molecules of water. If you only have one of something, we don't write that coefficient. Here's just a larger version of that graphic showing the difference between subscripts and coefficients. Another thing that's important to review here is the difference between a molecule and a formula unit. Typically, when we have covalently bonded substances, we say the term molecule. H2O, CO2, carbon monoxide, those are molecules and they stand alone. A formula unit is the smallest unit of an ionically bonded substance. So for instance, a salt crystal is a repeating pattern of NaCl, NaCl, NaCl over and over again. But we just record it as one formula unit of that ionically bonded crystal, NaCl. Other things that you might see in a chemical equation would be indications of the state of matter. So if you see an S in parentheses after a formula, that's telling you that that compound is a solid. An L would be a liquid. AQ means aqueous. That means that that substance is dissolved in water. And then G would be gas. You can see examples of this down here at the bottom. All right, now that we've laid down some parts of the chemical reaction, let's take a look at some different ways to interpret these equations. One way we can do this is looking at a chemical equation and trying to convert it into a word equation. So for instance, this first substance here is propane. This next term is oxygen gas. And we're producing CO2, which is carbon dioxide, and H2O, which is water. So a word equation for this chemical equation would be propane gas reacts with oxygen gas to produce carbon dioxide and water. Part of this goes back to knowing how to name covalent and ionic substances, which we've talked about in an earlier unit. One thing we should do when we look at these equations is take an atom inventory. We need to kind of use the yield sign as a dividing line and look at the left and the right and ask ourselves, is the law of conservation of matter being upheld? On the left side here, we have 3 carbon, we have 8 hydrogen, and then we have 2 oxygen. On the right side, we only have 1 carbon, we have 2 hydrogen, And if you look, we have 2 oxygen here and 1 here. That would give us 3 total oxygen. So then this bottom question is this balanced? Is the law of conservation of matter upheld? And the answer is no. We started with more atoms, so we need to fix that. So as we said earlier, we have to make sure the atoms that we start with are the atoms we end with. Matter is not destructible. The process for doing this is pretty basic, with small little things that you need to remember. First, you cannot change subscripts. I can't change H2O water to H3O just so it's balanced. I can only change coefficients. I can only increase or decrease the amount of a specific compound. So the first thing you're going to do is check to see if it's balanced. Then you're going to balance polyatomic ions, metals, then nonmetals, and we're going to save hydrogen and oxygen for the end. Typically speaking, if you balance those other 3 things first, polyatomic ions, metals, and nonmetals, the hydrogen and oxygen tend to kind of work themselves out. And then after we think we have it balanced, we should do another atom check to make sure we have the same number of atoms on both sides. All right, let's try some examples. The way I have students do this typically is I tell them, use the yield sign as your dividing line. It's the before and after. And then list the elements down the middle of that dividing line. So we have potassium on both sides, we have chlorine on both sides, and we have oxygen on both sides. Now we should do our atom count. We have 1 potassium on the left, we have 1 potassium on the right. We have 1 chlorine on the left. We have 1 chlorine on the right. We have 3 oxygen here and 2 oxygen here. So at this point, everything's balanced but the oxygen. So now you should be asking, what do I need more of and where? We need more oxygen on the right side. So I could put a 2 here, but you can see on the left that there's a 3. That should indicate to you that the lowest common multiple between those 2 terms is 6. So really, the coefficient of 3 here is probably what's going to fix this for us. And then what we do is we take 3 times 2, and then we'd have a total of 6 atoms of oxygen on the right. Now we need 6 atoms of oxygen on the left. So if we put a coefficient of 2 in front of this compound, that will give us 6 oxygen. But there's a problem. That coefficient also changes the number of potassium and the number of chlorine to 2. That problem's fixed pretty easily because we can put a 2 on the other side in front of this compound, and now you can see that we have 2 potassium, 2 chlorine, and 6 oxygen on both sides. This is balanced, and we are done. Let's try another one that looks a little more complicated. A lot of times students will look at these and think, there's no way I'm going to be able to solve this. But here's the thing. If we keep the polyatomic ions together, it'll make this a lot easier. Let me show you. Barium is the first thing we're going to write down because it is the metal on this side. But we're going to keep this NO3 together because there's NO3 on this side and NO3 on this side. So we're just going to keep it as one thing, the polyatomic ion of nitrate. We're going to do the same thing with sodium and sulfate, SO4, because there's SO4 on both sides. So we just went from a lot of different elements to now we only list 4 because we're keeping those polyatomics together, and it makes this more manageable. Let's do our atom count. Something to keep in mind, notice for nitrate on the right side, I only put 1. This 3 is not how many nitrates we have. That 3 is part of nitrate. I only have 1 nitrate. If I had more than 1, it would look like this, where it was in parentheses, and a 2 would be on the outside. And that's why I put 2 nitrates on the left. So if you look here, the only thing we need more of is sodium and nitrate, and those are combined in a term on this side. So if I put a 2 here, that's going to change the nitrate and the sodium to 2, and this is already balanced. This looks initially like something very intimidating and very difficult, and actually it's really simple to make balanced. All right, let's try another one. We've got zinc, hydrogen, and chlorine. This one is another one that's pretty simple to balance. If you look at the left, you can just put a 2 here, and that is a balanced chemical equation. All right, last one with some polyatomics. In the same way as one of the earlier equations, we have a 2 and a 3. That 2 and a 3 are only going to meet up in a lowest common multiple of 6. So we know that in front of this guy here we need a 3, because 3 times 2 nitrates will give us 6 nitrates. but this will also give us 3 nickel. On the right side, we have 3 nitrates, so a 2 here is going to be 2 times 3 and give us 6 nitrates, but it'll also give us 2 aluminum. But from this point on, it's pretty easy to balance. I need 2 aluminum on the left, so there's the 2, and I need 3 nickel on the right, so there's the 3. And now we've balanced that chemical equation. Balancing chemical equations is going to take some time to master. Keep working on the practice problems, let me know if you have questions, and we'll see you soon.